Hello everyone, I am glad to introduce our work, Depth-Aware Test Time Training for Zero-Shot Video Object Segmentation. This is a joint work of University of Macau, Tencent AI Lab, Intel and Dust, and Chongqing University of Posts and Telecommunications. Zero-Shot Video Object Segmentation aims at segmenting the primary moving object without any human annotations. Mainstream solutions mainly focus on learning a single model on large-scale video datasets. Despite being trained on the most widely used public dataset, about 3,500 videos, the deployed models often fail when confronted with real-world scenarios. In this work, we introduce a test time training strategy to address the problem. Our key insight is to enforce the model to predict consistent depth during the TTT process. During the test time training, the model is required to predict consistent depth maps for the same video frame under different data augmentation. The model is progressively updated and provides more precise mask prediction. Our entire framework is designed following TTT ROT. During the first stage training, which is denoted as training time training, DOT is trained on a large-scale dataset to perform two tasks jointly, primary moving object segmentation and depth estimation, which are realized by the main task decoder and the depth decoder respectively. During the TTT, the model is required to produce consistent depth maps between two augmented samples. The error is used to update the image encoder. Finally, the new model is applied to infer the object. Given an input frame and flow, we first extract their features through an image encoder and the flow encoder. The encoded image and flow features are aggregated to predict the primary moving object through the mask decoder. The depth decoder estimates the depth map using the image features. We use the depth maps obtained by off-the-shelf monocular depth estimation methods as pseudo-ground truth. We also introduce a depth-aware modulation layer, which enables features in the mask decoder to receive information from features in the depth decoder. Given a test video with T frames, we conduct TTT to update the image encoder by optimizing consistent depth map between a single frame under two data augmentation. The updated image encoder is expected to be beneficial for the mask prediction. Precisely, for the ITH frame, we obtain two augmented images by applying different data augmentation on the original frame. Then for TTT, we seek to optimize the consistent depth between these two augmented samples. We also explore different TTT strategies. First, the previous JVOS methods directly apply the trained model to infer the test video. Second, image-based test time training methods fine-tune the model on each individual frame. Then, we introduce video test time training by momentum-based weight initialization, which trains the model based on past models. Finally, we present video test time training by looping through the video, which further benefits from the global information. We evaluate our model on a variety of datasets. 4 prior methods for test time training, including TENT, BN, TTT ROT, and TTT MAY are used for comparison. It is observed that these methods do not yield substantial improvements in JVOS. In the context of JVOS, cues derived from 3D information prove to be advantageous, which explains the stable improvements exhibited by our proposed method when applied to test data. One crucial challenge in TTT is the additional time required for training. The performances are significantly varying in different strategies. We investigate the impact of training epochs on performance. As the number of training epochs increases, the disparity between TTT LTV and other schemes, TTTN and TTT-MWI, becomes pronounced, indicating that the proposed approach requires less time to adapt to a given video. We show the results of the pre-trained model in the top and the results of our DOT in the bottom. It can be seen that the results obtained by the pre-trained model are less accurate, and become better and better with our DOT. In summary, we introduce depth-aware test time training for zero-shot video object segmentation, which allows a pre-trained model better generalize to unseen scenarios. We propose a joint learning framework that simultaneously addresses object segmentation and depth estimation. During the inference, the consistent depth for the same frame under different data augmentations serves as the criterion for updating the model. Furthermore, different TTT strategies are explored. The experimental results demonstrate the effectiveness of our proposed approach in comparison to SOTA TTT approaches. We also achieve competitive performance compared to other JVOS methods.